Let's talk about this situation. Not actually on the right one. Did you determine that this was a binomial setting?
Yeah.
How did you determine that?
Because it has two outcomes, correct and incorrect. They're independent because one answer
Yes.
different to the other, and there's a set number of the 5 trials and the probability.
How should we outline this? Use your bins model and defend each piece. So B, success equals correct, fail your equals incorrect. The sense of binary would be there's a success and a failure. Those are your two options. Independent. Are they independent? Yes. Trials don't depend on one another. N? What is our N? That's the number of trials. There's 5 trials. And then S, what does S stand for? What does that S stand for? Same probability. Do they each have the same probability? And so we should define it. Say something like this.
Because like when I read that initially, I was like, I thought I meant like 0.5, 0.5. Like what is it? In what sense is it?
Same probability of the success in each subsequent trial.
Okay.
So there's a 1/4 probability of success in each subsequent trial. In the case of a flipped coin, what would be, so let's say Gigi wants to get heads when she flips the coin. So her success is flipping heads. What would be her probability as defined in this S category? It'd be 0.5. And each subsequent flip of the coin, is it the same? Yes, it is. So in that case, the probability of getting exactly 2 correct would be the probability of X equals 2. How did you define this on yours? Be brave, Little Toasters. Have you guys even seen that movie, The Brave Little Toaster? That's not a thing anymore. It's fine.
And 5C2.
We have 5 trials. We want to take any combination of 2 of them. So 5C2 times what?
0.25
Our success rate
to the second power.
to the second power times 1 minus 0.25. So you could put 0.75. That's our failure rate to the third power. As a review, somebody help me understand some of the nuances of this formula that can help us make sure we've got it correct.
The top 2 numbers, the exponent should add to the total number of trials.
Because it's binary, exactly. Because it's binary, you either success or fail. So the number of successes plus the number of failures have to equal your total number of trials. What else is another feature of this?
Probabilities have to add to 1.
Because there's only 2 probabilities, the probabilities have to add to 1. Very good, yeah. And then our combinatorics out in front need to reflect how many successes we're trying to get out of how many trials we have. Is there another way to write this?
Yes.
It's a variation of the notation. What does it look like?
5. Oh, yeah, 5 and 2.
This is acceptable. 0.25 squared times 0.75 cubed. What is our answer? 0.264. You've got a 26% chance of getting 2 right. So Hill, nice work, man. You got it. Anybody else have 2? Nope. There's a way to do this on your calculator. You want to know it?
Yes.
Here we go. It's called Binomial, and this one is going to be PDF. Remember we did normal CDF earlier in the year to find a cumulative probability underneath a curve? Well, in this case, we're going to find a cumulative probability of a binomial setting. To use this on the AP test would be to show that it's binomial, define your probabilities, and then find this function. So this is actually going to be under the vars menu. So go second vars, I think it's distribute, and then you go down, I believe it's A. What it's going to ask you to do is to put in your total number of trials, the probability of success on the trial, and then the number of trials you are trying to determine as the favorable event. What that looks like when we write it up here is a comma-separated list. 5, 0.25, 2. What do you think we're going to need up here? We're going to have to label. So what we should do is do binomial, CDF, sorry, we'll do CDF in a minute, PDF, 5.252, and you can go like this. And this is the number of trials, this is probability, and this would be like successes.
What's the X value? Is that what we're trying to get to, right?
Yes. This X right here is the number that you're trying to get correct. That actually goes here. Fill in the table below showing the probability of getting exactly, that's a key phrase, exactly X correct. So in our case, exactly 2 would be 0.264. That's just what we calculated. I'd like for you to practice using binomial PDF to find the other probabilities in the table, please. So let's chat. Here's what I got. What do you notice? And this is maybe obvious to you, but I don't want to overlook it. What do you notice about the numbers in the chart? They decrease. Why would they decrease? It is. It's very difficult to guess all 5 correct. Whereas maybe it's a little bit easier to get 1 correct. I think this is kind of interesting, right? 1, more likely to get 1 than it is to get 0. Because you'd have to guess all of them incorrect. Right? So the most common one would be that 1. So be that as it may, let's find and interpret the mean. What do you think this looks like? This is a review of like section 6.1. How do we do it? We're going to find the sum, because really isn't this just a probability distribution? So we're going to find the sum of all of our values times all of our probabilities. And we're going to label that the mean of X. Go ahead and try that.
I have a question.
Slowpoke.
Wait, this sum of...
Also, I was not calculating the entire time I was asking that question.
Shots fired.
So,
Wait,
Really?
how do you do that?
What is
one?
the X?
What do you enter?
It's like
Oh, you do. Hey, so this is a good question.
I did the
You do
version.
0 times 0.237 plus 1 times 0.396 plus 2 times 0.264 plus 3 times 0.088 plus 4 times 0.015 plus 5 times 0.00. You could use 0.001. What you end up with is about 1.25. Conceptually, they want us to interpret this, but in your mind, just kind of boil it way down. What does this mean?
The quiz was taken many times. The average amount of correct answers.
If the quiz was taken many times, the average number of correct answers would be about 1.25. But Mr. Saris, you can't have 1.25 correct answers. How is this your answer? Should I round it? Should you round it?
It's the sum of
Right. You shouldn't round it because you're looking at the average number of correct answers. So conceptually, this may not make sense because you might be thinking, how could I possibly have 1.25 answers? It's the average.
Is that like when they say in a country they have like 3.7 kids?
Yes, it's exactly that. The average number of children in an American household is 1.7 children. Okay, great. You can't have 1.7 kids, but together the average speaks for itself. Now,
Which might not be alive.
so
But there always has to be one.
not sure how I feel about that. So, does this answer, and this you're considering it reasonable, does this answer seem to match what we found in the chart?
Yes.
It does, because why?
It's skewed right, so it tends to lean that way.
So that's where our big probability is. Yes.
So do you not have to say if the quiz is taken randomly many times?
No.
Okay.
So what's the probability of getting at most 3 correct? How are we going to figure this out? So work on number 6 and work on 6, 7, and 8. So find the standard deviation and then find the probability of getting at most 3 correct and then find the probability of getting 3 or more. So do 6, 7, and 8. I think some of you came across the correct answer. If you remember, hold on. Oh, do you need another minute?
Yeah, that's in stat.
Okay, so you don't find the sum of this?
It's on the list.
So now that you figured that out and you have all the lists, let me show you a little formula here. What you should have gotten is you should have come up with the standard deviation of x equal to 0.968. There's a formula for this. The formula looks this way. You take the standard deviation of x is equal to the square root of your number of trials times your probability times 1 minus the probability. Try it.
And its number of trials.
Number of trials. Number of trials.
Sorry, what was
So much easier.
P is your probability.
So much easier.
I didn't get that one.
Did you get it?
What?
Yeah. Okay.
Is that how you can do it just like for everything? Or just
Man, Mr. Saris, why? See how great your appreciation is of this? I want you to take out your formula sheet that I gave. So the statistics formula sheet. I want you to flip to that second page where we start to talk about all the probability formulas. Do you see it on there? And when you look at this sheet, sometimes it's easy and you're like, oh, I have this formula sheet, and it becomes decontextualized. You're like, well, I don't know when to use it. Do you see why understanding the binary situation is so important? Because it's under the heading. What's the heading there? What does it say? If x has a binomial distribution with parameters n and p. So they don't tell you what n and p stand for. You have to know that. They can't tell you if the situation is binary. But Jared, when you get to the test, you determine that it's binary. You know that n is number of trials and p is the probability, which is the same for each success. Then you have this wealth of formulas you can draw from. You can find and look right above that. What do you notice right above that? The mean. So in number 5, out in the margin, check and see, is the mean of x, we just calculated it, right? We did that sum of all of the probabilities times all of the x values, is the mean. So up here you should put the mean of x is equal to n times p. Does it work? 5 times 0.25, did it give you?
Yes.
Man, look at that.
Oh, that's rude now. Okay, that's more.
That's productive struggle. So you productively struggle through this. Now you have this formula, but you've done it. You're familiar with where it comes from.
homework's gonna be so much longer than it
What
has
is that
to
top
be.
left that even say?
It says the mean of x is equal to n times p. I did it in the context of our problem. Number of trials was 5, and our probability of each trial was 0.25. So 5 times 0.25 gave me 1.25. Let's look at number 7. Probability of getting at most 3 correct. Tell me, what did you do to get this? At most 3.
Oh, I haven't done that because I
Oh,
spent
yeah.
so long
I
doing number
did that.
6.
Okay, so let's talk about it in general. One could add up the probabilities of what?
One right?
X equals 0 plus the probability of x equals 1 plus the probability of x equals 2 plus the probability of x equals
1 minus 4.
3. So you could do 1 minus the probability of 4 and 5. Now, it works for this, right? There are only 6 outcomes. What if we had 10 outcomes? Annoying.
Sad.
Enter binomial CDF.
Yes.
So binomial CDF, much like normal CDF, calculates at or below. Some Please make sure you understand this. PDF is the exact number. CDF is at or below, x equals, and I put question mark, x equals number, like the number of trials that we want. So if it says at most 3 would be 3 or less. Our formula for this would be binomial CDF. Because CDF, you can think about it like this. The C stands for continuum. So it's a continuum of values. Does that help?
Yes.
Binomial PDF would be like a point, like right there, boom, just that one. CDF is a continuum of values. So the CDF, what are we going to put into our formula? Number of trials, probability of each success, where we stop. Either do these last 2 problems, so 7, 8, in light of knowing binomial CDF, or to check them using binomial CDF.
Did we use normal PDF?
We don't necessarily use normal PDF because you can use it, but it really, normally it's not. I want to record this because this is a great question. The question is, yeah, I got that, Mr. Sarah. So what we would say is, and I want to add something here. So this would be the probability of x is less than or equal to 3.
Can I just put 3?
Can you just do 1 minus?
This notation helps. So we could say this. The probability of x is greater than 3 would be equal to 1 minus the probability of
Binomial CDF.
1 minus the probability of x. Nope.
Isn't it greater than it is? It could be true.
Is this correct? This is right, right?
Wait, I thought it was
The
1
equal.
minus the probability
No,
of
it's
x
less-
being
it's
equal
equal
to
to
or
less
less
than
than 2.
3 or, oh, sorry. I
Unless
thought.
it's 3 or more, isn't it? This is what's... What?
Yeah, X.
Because it has to be
Yeah.
3
No, it'd be
or
X
more,
is
so
greater
doesn't
than or
it-
equal
doesn't
to.
3 get like
This
involved?
should be greater than or equal to.
Yes.
Oh, there we go.
So how do we calculate that?
Wait, so you have to do P, you have to do binomial CDF for 2 then, right?
Just plug it in.
Why does this work?
Because it's the same thing.
Add or below.
It's the same thing. So at or below. So what we would do is 1 minus binomial CDF. And this is what you should write. You should write this down if you're going to use it. And please do. Once you've identified that binomial situation, use this. So 1 minus binomial CDF. How many trials do we have still? What's our probability? And what goes here? In this case, our successes would be 2 because we want the complement of that event. So 3 or more would be not 2, 1, or 0, but 3, 4, 5. What did you get for this one?
Wouldn't it also work if you put like 0.75 instead of the 0.25?
Antonio. What do you think? Would it work?
But you have to flip everything.
So you have to flip everything. So if you make the success event the complement, then you need to make sure that you make the number of trials the complement as well. Because then you'd be counting like what would it mean for me to guess wrong? So don't confuse yourself too much.
So PDF is exactly something.
PDF is point. It's exactly that point. CDF is a continuum, meaning like at or below.
Do you have to put the probability of x is greater than or equal to 3 or less than or equal to 3?
You need to
That
put,
first little bit you put?
yes,
Okay.
you need to clearly say what it is that you're doing. I added these 2 pieces, and I might have confused you a little bit more because I missed that first little symbol. But then it's important to make sure that you get to a point where you're saying the probability of this is the number of trials that I'm intending to talk about.
I got, oh wait, JK.
Yes.
So why is it the 1 minus? Why is the successes 2 since you can get 3, 4, or 5?
Because 100% probability covers everything. And you want to subtract the probability that you get 2, 1, or 0 correct, because you're saying everything that's possible minus the stuff that I don't want. The stuff that I don't care about is if a person got 2, 1, or 0. And what's left would be the probability of 3, 4, or 5.
Wouldn't that still be 3 then because you can get 0 right, 1 right, or 2 right?
Yes, but that's 3 values. But in here goes the number of successes.
Oh, so it wouldn't count 0.
It would count 0, but this would be 2 out of 5 correct, or 1 out of 5 correct, or 0 out of 5 correct. That's a good question. Can we sum it up in the box here? I'm not going to put anything new in this box that we don't already have in the margins. This is just kind of a compiling of what we're using in these formulas. The title, the heading is going to be Describing Binomial Distributions. Describing binomial distributions. How do you think you'd describe the shape of a binomial distribution? Does it have to be? This is a trap. It could be skewed, it could be symmetrical. So what do we need to do to be able to determine that? You got to sketch it. So you got to make a histogram. I baited you there, I'm sorry.
I was going for like really big concepts.
Right.
And you were like, just sketch it.
Just sketch it. You got to sketch it and talk about it. Because the likelihood could exist that it's any number of things, but you need to look at what it looks like. The center, what's going to be our measure of center here? What have we been talking about as a measure of center? Mean. Let's define that formula. The mean of x, you can think about it in terms of a couple of different things, right? What could it be? It could be n times p or sum of x sub I times p sub I. Probably which one are you going to want to use? Probably NP.
So what do you do for that? You just add all of the probabilities?
For this one?
Yeah.
No, you multiply your number of trials times the probability.
5 times 0.25.
That's right. Mm-hmm. And it matched, right? Because when we did the sum, we got 1.25. This one gave us 1.25 also. So then our variability, what are we using as our measure of variability here? We're using standard deviation. We now have a formula for standard deviation. Well, we have a couple formulas, right? Let's make the simple one because the previous section we had the longer one. What's the formula for standard deviation that we're using now?
NP times 1 minus P
Square root of n times p times 1 minus p. Oh, voice crack there. Sorry, everybody.
And why did we learn the big long one?
Why did we learn the big? Why did we learn the big one?
That whole chart. we
No,
drew.
it's so true.
What was the
I-
bad one?
That
So,
chart, the table.
One could say that bad to appreciate the good, but I really want you to hammer in on standard deviation having to do and coming from every single value's relationship to the mean. Because sometimes we get so far past it and we forget that when I talk about standard deviation, it's for a group of data, but it was calculated by every single piece being compared with the mean. Does that formula help you appreciate it? Maybe. Maybe. At the very least, when you're doing it, you're like, man, I have to do a lot of things. Yes, standard deviation does involve a lot of things. It involves every single piece of data on the list. Don't talk about the number of trials. You want to use many, many, but you don't want to talk about the specific number of trials. Go ahead and practice this using the check your understanding. So I'm going to ask you to do each of these things. You're going to have to sketch a graph. You're going to have to find the center. You're going to have to find the variability. But the difference is here, I'm actually not going to give you, the chart. You're going to have to make the chart. So you're going to have to do a little bit of practice with your calculator and the normal or the binomial functions. Let me give you some time to do that. For a second. So we determined that it was binary. And in this specific situation, we need a histogram. They didn't give us the chart. They didn't give us a histogram. So what's going to go along the bottom here? Correct answers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where am I going to get those values? You have to calculate. Yes, you got to calculate them, right? And so let's set up the formula one time, and then we can replicate. Help me set up the formula one time. Or what did you do to get, for example, 0?
Wait, why don't you just put a 1/5 on the y-axis and then draw a straight line? And then drop it and
It's
change
not the
it.
same.
Oh yeah.
Yeah.
That's what I did at first, but it's not right.
And then be forgetting like that one correct.
What did you put in number 1 as your number of trials? What did you put as your probability?
Like 2.
My probability is 0.2. To get the probability of 0 correct, help me out here. So the probability of x equals 0 would be what?
10 over 0.
So 10 of the questions, you got 0 of them right. Times what? 0.2 to the 0 times 0.8 to the 10. Is there another way to do that?
Yes.
Yes. What would be the other way to do it? Or, you see how we're tying this all together now? And you're about to realize how much work this is going to be?
Oh, the continuum.
Binomial, is it continuum?
No, it's just P.
In this case, so this is just a point. I just want this bar, and then this one, and then this one, and then this one, and then this one. So I'm actually going to do binomial PDF 11 times. So binomial PDF, but I'm going to show you, I can show you a little shortcut. What goes in my parentheses?
Trial.
10 is my trials,
Point two,
probability is 0.2,
0.
then 0, and then 1, and then 2. How do I determine the height of my bar?
Answer.
This is the probability. So whatever the probability is, that's how high the bar is. What did you get for 0?
0.107.
0.1, 0.107. So I'm going to go Good. 9% done. An easy way to do this would be to do second enter. That's entry, right? On your calculator. So second enter, and then change your number of your number of successes to 1. What'd you get for your probability on 1? 0.26. So my graph obviously has a bunch of values here that are very low. When I'm determining shape and center, I'm not necessarily needing to know all these tiny little values. There's value in histograms. Really what I'm trying to figure out is what is the shape of this? Skewed right.
Wait, I have a question.
Hold on 1 second. What else do I need to determine? Peak at 2. Skewed right with a peak at 2 is what I should say. That's a description of the shape. Did I need to do all that work to determine the shape? No, but now you know where a histogram for a probability distribution comes from. It comes from calculating each individual probability. Now, if I had asked you to do this, ba-boom, for every single one of those, 3 weeks from now when we all got done, we'd all high five around and have a graph. Well, so you're shortcutting this using your formulas. Okay, ask your question now.
So I get like how the mean follows the skew in the goal situations, and maybe it's the same thing.
As compared to median.
Yeah.
Yeah.
And like that's like the same situation here, right? Because like the mean follows the skew. I mean, I feel like.
So let's think for a second here. What's a follow-up question that we could ask? How would we determine where the median was?
Or 0.5.
Where is 0.5? Did you catch that? Where would 0.5 be here? Like 2?
Or maybe like between 1.
So somewhere in here, yeah? So let's calculate and interpret the mean of y. So the mean of y, what's my formula here? N times p, which would be 10 times 0.2. Show me the math. 2. Did the mean follow the skew in comparison to the median? Yeah.
Wait.
Now we don't specifically know where that median is, right? But at the same time, let's calculate and interpret. So we have to interpret the mean. How do we interpret this? After many, many quizzes taken, the average number of correct answers was 2. And we could say answers out of 10 was 2. That gives us a little bit more context.
Like
Oh, 2, great.
20,
What's that?
a 20.
A 20. Standard deviation?
So rare if you got a 100.
But it would be an anomaly. It would be significant.
It would be significant.
Then
So
point.
statistically
It would be. It would be.
0.0000001.
I saw a statistics T-shirt the other day. No comments, please. It said significant. That's all it said. I was like,
Where did you find that?
yes. Online.
You should buy that shirt.
And you know, just wear it every
We
day.
should all get a different statistics shirt and then have stats day and just like wear.
Yeah. Wait, what's like a significant number? You know how like chemistry is mole day?
Yeah, that'll keep people.
What's
from
like
Wear it the
stat?
5th of every month for 5%.
Yeah.
There we go.
I'm down for that. We get
But is
Jeans
there like a
yeah.
Jeans
is
Day
there
on
like
the
a
5th of every.
constant-
Me at
Is there
home
like
on the
a
couch
C
on
or
a fifth
something?
Saturday watching
You know how
TV and
C
like
like
Yeah.
the NCK?
Let's find a nice little coefficient and we'll correlate it. We'll get a stats t-shirt. We'll do it. Okay. Standard deviation n times p times 1 minus p. Take the square root. 10 times 0.2 times 0.8 square root. What do you got? 1.26. Let's interpret that. I've been skipping that question today for some reason. I just have not respected that question at all. Interpreting the standard deviation. What's the standard deviation? How do we interpret it?
Average number of correct answers typically deviates that number.
Typically
Is
varies.
it average?
So the number of correct answers on a quiz of 10 questions typically varies from the mean of 2 by 1.26.